And the point of all this is to learn the patterns of polynomial functions. And so we're doing a bit of analysis here. And the analysis I'm doing, the shapes of these functions, unfortunately you have to take my word for it. These shapes can be determined through methods of calculus. So that's the best I can tell you. If you take Calculus 1, you'll know exactly why they're shaped the way they are. All right, so degree 3 equation is called a cubic polynomial. It has the form y equals to ax to the third power plus bx squared plus cx plus d. And its name is cubic. The shape is called cubic also. So from here on out, the name of the shape is the same as the name of the function. Cubic, quartic, quintic, those are the kind of words we're going to run into. All right, now it tends to go, or can go, like this. All right, so it can go up, come down, go back up again. Now it could also come down like this. And I think I have one of these under my sink, actually. But, oh well. Yeah, I've got one of those under my sink. All right, and you probably do too. Just look under there if you have no idea what I'm talking about. Okay. All right, so there are up to 3 roots. Actually, there's at least 1 root, because at one end, it's going to go down to negative infinity. At the opposite end, it goes to positive infinity. And so now it could be reversed. It could be positive infinity here, negative infinity there. But the graph is connected between the infinities. And so somewhere along the line, it's going to cross the x-axis. So it's going to hit in at least one place, has at least 1 root, but it could have up to 3. So it has 1, 2, 3 roots. And it has up to 2 extrema. So it has up to 2 extrema. It gets a little sticky here. Could you say it's between 0 and 2? Well, it depends on exactly how you define the extrema. It gets a little fuzzy here, but it has up to 2 extrema. In other words, there are up to 2 turns also. 1 turn here, 1 turn there. Now another terminology piece that I introduced in an earlier chapter was the point of inflection. And here's the point of inflection. So remember what that is. The point of inflection is a place where the concavity can change. So on the left side of the one I've drawn is called concave down. It's looped over. And then on the right side of it, it's concave up. And the place where that changes is the point of inflection, which is about right here. So this one has 1 point of inflection. All right, let me see if the camera's picking it up that low. Yep, we're in good shape. Okay, so I think it has to have 1 point of inflection regardless. Has to have at least 1 root. Has somewhere between 0 and 2 extrema, usually 2, but it can have fewer. Let me give you some examples of this, because as you build up in the degree of these polynomials, there can be a lot of variations to these themes. So for example, for the cubic, there's either 3 or 6 ways to look at it, depending on how you're counting things. So this one has this form. Then there's one that's kind of special, where it levels off here. It actually goes horizontal at that point of inflection, and then goes back up. And then it can be elongated like this, stretched out. So here are the 3 types, and if I flip them over, I now have 6 types. So there are actually 6 possible cubic polynomial shapes out there. All right, well, let's compare that to degree 4. I'm going to go up to degree 5, and then we'll quit at 5. And by then, I think you'll be starting to get numb over all this, and you'll have a pretty good idea what the patterns are. So, a degree 4 equation. Degree 4. is called a quartic. Quartic. And it has the form y equals to ax to the fourth plus bx cubed plus cx squared plus dx plus e. Fourth degree polynomial. And it could have this form. Down like this, up like that. All right. I tried to draw it so it was not symmetrical. All right. So let's see. There are how many roots? Well, it could have up to 4 roots. 0 to 4 roots. And you probably noticed by now the number of possible roots, the total number of possible roots, always matches the degree. All right, there are good reasons for that. How about extrema? How many extrema do you have? Well, there's one here, here, and here. So in other words, we have 2, in this case, we have 2 relative minimums and 1 relative maximum. So 3 extrema. I'm going to say there are 1 to 3 extrema. Okay. You could say there's up to 3, but there has to be at least 1. I know that. And how many points of inflection? Well, probably 2. Okay. I'm going to say 0 to 2 points of inflection. All right, so up to 2 points of inflection. So again, the inflection is where it changes concavity. Here it's concave up, and then concave down, concave up again. So that changed in 2 places. It could have actually 0 points of inflection. I think what you're probably starting to notice is that okay, the number of roots equals to the degree. The number of extrema can be 1 less than the degree, and the number of inflection points can be 2 less than the degree. Is there something else here that would be 3 less than the degree? There is a point, a unique point associated with the quartic that fits this pattern sort of, except I don't know what to do with it or what it would describe. So that's why I'm not going to bring it up. And I don't know if anybody's ever found a use for that single point, but you know how we're going 4, 3, 2, 1. What would be 1? Well, there is a point I could find that is has its own unique characteristic, and there's one of those. But again, I don't think it shows us anything geometrically that I'm aware of. Nothing very apparent, at least.